Hey there, welcome to our video abstract featuring an exciting study on the gadolinium and erbium tetraboride series. If you're interested in diving deeper into the details, feel free to check out the full text linked in the description below. We consider the ferromagnetic phase as anomalous observed in gadolinium and erbium solid solutions because the end compounds gadolinium tetraboride and erbium tetraboride are antiferromagnetic materials. When we examine the magnetic properties of gadolinium tetraboride, we observe reversible magnetization isotherms. This implies that the magnetization curves measured during the increase and decrease of the magnetic field overlap, resulting in the absence of magnetic hysteresis. The same applies to erbium tetraboride, but when we partially substitute erbium for gadolinium in the gadolinium tetraboride structure, a ferromagnetic phase is induced. This means that we observe magnetic hysteresis in the gadolinium and erbium solid solutions. Consequently, we can see the presence of a coercive field and remnant magnetization in the hysteresis curve. To understand why this is not a conventional phase, let's examine some physical properties of these tetraborides. Rare earth tetraborides are intermetallic compounds that typically exhibit antiferromagnetic ordering, with the exception of one member of the family. These compounds possess a tetragonal crystal structure, giving rise to intriguing magnetic and electrical properties. The magnetic rare earth ions are in the AB plane and embedded in a boron network, grouped into B6 octahedra and boron dimer pairs. In this tetragonal lattice, the rare earth ions form sheets perpendicular to the C-axis and lie within the AB planes, forming a frustrated Shastry Sutherland lattice comprising squares and triangles. Notably, the magnetic interaction among the rare earth ions in tetraborides is mediated by the RKKY interaction. In the case of gadolinium tetraboride, its magnetic structure exhibits a noncollinear character, with magnetic moments lying in the AB plane. Conversely, erbium tetraboride have magnetic moments oriented parallel to the C-axis. This disparity in spin alignment gives rise to distinct magnetic properties. The key parameters influencing frustration in this system are the antiferromagnetic exchange interactions, J1 and J2, occurring on diagonal and square bonds of alternating tiles. The interplay between these competing interactions, geometric frustration, and external magnetic fields leads to the emergence of a diverse range of magnetic states, including fractional magnetization plateaus, contributing to a rich phase diagram and other exotic properties such as the inverse magnetocaloric effect. Given these intriguing properties, research on these materials remains subject of significant interest. Then, we have synthesized tetraboride single crystals to investigate the rapid evolution of magnetic properties upon partial substitution of erbium for gadolinium. These single crystals were grown using the aluminum flux method. The grown crystals have these platelet-like polyhedral morphology. X-ray diffraction scans confirmed the formation of single-phase materials, and the unit cell volume decreased with increasing erbium content, indicating successful substitution of erbium for gadolinium within this series. The quality of the single crystals is attested by Lau photographs. The lack of distortion or smearing in the diffraction spots is suggestive of high crystallinity, with absence of defects or twining. With the increase in erbium content within the series, a noticeable decrease in the Néel temperature is observed, as depicted in these specific heat curves. This phenomenon is similarly reflected in the magnetic susceptibility curves. Another notable effect is the increasing anisotropy observed in the magnetic susceptibility curves. In the case of pristine gadolinium tetraboride, the anisotropy is evident only below the Néel temperature. However, for samples with 20% and 40% erbium substitution, this anisotropy extends to much higher temperatures. It is noteworthy that with just 20% of erbium in the compound, we observed a transition to the paramagnetic state induced by the field. Furthermore, for the sample with 40% erbium, an additional metamagnetic transition is also observed. In other words, with only 40% erbium substitution, the plateau phase is established as in pristine erbium tetraboride but occurring at higher magnetic fields within a narrower range. Finally, we observed the establishment of a ferromagnetic phase in both samples, with 20% and 40% of erbium being much more pronounced along the C-axis. Significantly high values for the coercive fields are observed along the C-axis, which coincides with the z-axis for erbium tetraboride. These intriguing features are likely due to the competing anisotropies. To further elucidate the origins of this interesting behavior, a comprehensive investigation of the physical properties of these single crystals is currently underway. That's all for today's video. Thank you for watching.